So I'm not going to read through all of this, but big picture as you start, I mean, we still have a third of the class to go. I've got some things to show you yet, but really what you're going to do is go get data. And notice I said here between 30 and 100 data points, and actually you'll understand today why I'm saying 30. And your collection of that can be you find it on the internet, or it can be you gather it yourself. I definitely don't want that to be complicated for you. This should not take very long. Like I'm thinking this is I don't know, 2 hours of work, 3 hours of work. Like you should not be spending 10 hours on this. This is, I mean, it's worth some points. It's in the grade book and so forth, but it's not something that, it's just really a chance for you to kind of show what you can do at the end of this class. And again, you're not on your own. You can ask me questions about it and, you know, ask me something about chapter 1. You forgot about it. You can say, hey, would you look at this? Did I do this right? I want this to be a teachable opportunity for you. Second thing I'd like you to think about is, you know, you are going to hunt for a job at some point. And wouldn't it be cool if you could show them something you could do? Like, don't see this as just satisfy this stupid teacher that wants to make us do a project. See it as I'm going to make something that I can, you know, put on my resume, if you will. Again, this is the kind of thing, if you show sort of a mastery of an Excel and an ability to do something, that's kind of a cool, powerful skill. And that's what I'm after in this class. I want you to pass, but I want you to actually be able to do something. So your paper, which is really short, should explain 3 aspects of a statistical design. Chapter 1, we looked at data and just quickly how you gather it, what type of study, where is the biases in collecting your data. If you sent it out to Facebook, that's not going to be good data, but it's okay. Like I don't want you to make it complicated. Again, I don't want you to stand on a street corner and make this complicated, but just be aware of it. Like, you know, I gathered my data in a way that would be more effective if we did it this way, but it would cost more time. Just have some sense of, you know, where did you gather your data and what is it you're studying? What is it you're trying to figure out? And then chapter 3 through 4, basically just descriptive statistics, describe that, mean, median, mode, that kind of stuff, make a bar graph of it and so forth. And as I said, bar graph, pie chart, table, and all the descriptive statistics like mean, median, and mode, those kinds of things, standard deviation and so forth. Look for outliers, you know, those kinds of things. And then lastly, inference, which is kind of predicting the future. So the first part of this class was kind of reporting, hey, here's a nice picture and a bunch of summary sort of numbers for this individual numbers like mean and standard deviation for this giant pile. That's really cool. But then inferential statistics, what we're studying kind of right now and have been starting to study, is where you make predictions. We made predictions on the last test about, you know, what % of people are gonna, for instance, have a birth gestation period between these 2 days. We made a prediction about what that would be, which allows you to do something helpful in the future. And so that's kind of the big picture of what we're studying. Notice I said here, your paper should start by posing a few relevant questions. In other words, the ideal thing is you have an interesting question in your mind, something that you would like to answer. And then you go gather data to kind of have something intelligent to say about it. I mean, keep it simple. Like make sure you walk out of here understanding what statistics really is. And then I'm telling you down here kind of where your grade comes from. 5% for making all the calculations you could make. 30% for some sort of a professional presentation of the data in the graphs. 50%, which I think makes sense, for the accuracy of your calculations. Do you actually correctly know that there's, you know, outliers, mean, standard deviation, so forth. Let me just show you a couple of examples. Again, I'm saying this now because what would help you is if you took the time to maybe start thinking like, what would that data be? Where would I get it? So just read this through, get a sense of what's going on and start plinking away at it. In a sense, you could actually make 2/3 of this project right now. You can't do the stuff we're studying right now, but again, it'll just keep it from being some big burden at the end of the class, because, you know, the end of the class comes, we've got a last test we got to take, we're preparing for that. And then there's some presentations in there for one day. And so, you know, that can feel like a pile if you sort of wait till the end. So just some friendly advice. Couple quick examples and we'll be done. Let's see, screen. So this is just some from last term, fall. Notice, and I just kind of picked these randomly because I thought they were kind of decent examples. I'll show them to you super quickly, but 2 people did a PowerPoint. This person did a Word document, and these 2 people did Excels. I did say on yours, because the Excels were not very professional looking, I sort of upped it a little bit. And maybe you can appreciate that if you should do most of your calculations in Excel just to make your life easy. You're more than welcome to type it all on your calculator. Don't care where you do it. But of course, the bar graph in Excel, there's no way to get it out. There's no way to get the statistics in a way that's presentable if you don't do that. But as an example of a Word document, why the Word document's a little bit better. So notice this person, they looked at the amount of human traffic cases reported in the United States in 2019. So they did not gather their own data, they just went online. And as we said before, there's 50 states. And so if you ask any questions about what's going on in each state, that's always a good place to get 50 data points. And so she just explained where I got that data and so forth. And so that was interesting to her. So, gave a website as to where it came from. And then I guess what I'm interested in you seeing is, notice, because it's a Word document, it gives you the ability to type stuff. I mean, you're going to have to say a few things about where it came from, and it's going to look way more professional here than it is in Excel. But you can probably appreciate, or at least tell from looking, this is copied and pasted either off a website or from Excel, from her Excel. And so this was kind of the raw numbers. This was basically her list of numbers. In the end, that's what your final project is. Go get a list of numbers from somewhere. Gather it yourself or get it online. And then crunch it. So, she found kind of a cool graphic that actually showed all those numbers sitting on the American states. And then she made some classes and made a bar graph. And of course, again, you can appreciate, yay, that's really amazing. Looks like the strong majority were somewhere between this many cases, and it was really unusual to have that many cases. Notice one thing that's lost in this case is you don't know what state it came from anymore. But if you wanted to, it was still listed above. But again, can you see that as a graph that was made in Excel? You should know how to make those now. And she just copied and pasted it into here. And then a whole bunch of data. She found the mean, she found the population standard deviation. Why'd she choose the population? It's all the states. Yeah, so it actually she had a population. There's the 5-number summary that you understand. She figured out the lower fence, the upper fence, and discovered, based on the upper fence being 517, that she had 3 outlier states. And then what I just introduced briefly to you yesterday, she listed a confidence interval. In other words, she got a mean of 260.92, but you're not, because that's a sample mean often with statistics, because you took a sample, it's an admission that there's some error in that sample. And so although she got a sample mean of roughly 261, she said the real mean is actually, well, I'm 90% confident it's somewhere between here. And notice that's a massive range. In other words, she's saying it could be as low as 182. It could be as high as 340, the actual mean, the real mean. Now, again, this is a little weird in her case because she actually had population data, which means that 260 is correct for 2019. Does that make sense? So you didn't have to guess. But the point is, you should recognize everything that was done there and actually feel reasonably comfortable with it, with the exception of just this last thing, which is what we're studying right now. So again, my advice, get started on it. A couple people took it up a notch. This person was, and I think this is a wonderful question. This person was interested in mental health about COVID. Again, I think that's a wonderful question. Is this like, what effect has that had on people? She's just curious about it. Does that just thrash people to be alone, walk around with masks on and all that kind of stuff? Notice hers is a PowerPoint presentation and it looks really cool. Again, if I'm hiring and somebody says, hey, look, I did all this number crunching and I made it look really cool like this. Wow, that's impressive. You can do stuff. That's awesome. In her case, she actually made the survey herself, and if I remember right, she sent it out to, I forgot, maybe it'll say here somewhere. I'm not going to take the time to read all of this, but she sent it out to, I want to say, her own Facebook people or something like that, people she knew. Again, does that make sense? That's not the greatest way to do a study because it's only people that you know. And so maybe they're like you, and can you appreciate that, be a little biased? But again, I want you to do that because it's easier. I don't want you to, figure out some way to go survey, real random people, because that would take forever. Just notice that it, maybe the conclusions aren't as good as they could be because your sample's a little biased, and get on with it. Because that was easy for her. It was super easy to send out a survey question. And in her case, she gave a 0 to 4 scale as to whether, people were, whether their mental health was affected. Oh, here it is. She shared it on as a Facebook page. So it's something she shared on Facebook. So it's a Facebook connection. And again, so because her score was 0 to 4, it was kind of a question of what's the average mental health. Notice she got 2.545 for the average score that people said between 0 to 4, and she listed both standard deviations. She probably should not have listed the population because that was definitely not a population. She just asked people, but does it hurt to add an extra calculation in there? No. Median, mode, quartile 1, quartile 3, so the 5 number summaries down here, she listed her outliers. Notice because her scores were possible from 0 to 4, she got lower fence of -1, upper fence of 7. You can't get numbers outside of that, so she would have had no outliers. Notice there's a typo there, our liars. Could have caught that because it turned red. And then, again, notice the kind of the cool stuff of this is there's the display. Like nobody wants to see this list of 70 numbers that she got, but notice that's kind of interesting. And notice I think it's even kind of cool that she even, kind of told us down here what those numbers mean. So 0 was they noticed no change in their mental health because of COVID, didn't care. 1, change, but not necessarily due to COVID. 2, slight change. 3, significant change. 4, drastic change. Again, isn't that kind of interesting that 19, like the 2 tallest bars here, were people saying on Facebook, whoa. Now, again, another problem with Facebook is who responds to surveys on Facebook. I mean, maybe you're on Facebook, but it's like, I don't respond to that stupid survey. If you're the type of person that responds to a survey, does it make sense there's bias in that? Maybe the type of person that responds is more inclined to be emotional and, have lots of ups and downs. And, so you see what I'm saying? It's like, this isn't perfectly reliable. But the idea here is just to practice. I don't really care where your data comes from. Recognize that there's some shortcomings in how you collected the data. And therefore, can I rely on this? Can I go to a Senate hearing in Washington, D.C. and show, look, things are terrible as a result of this? Well, maybe not. So that's kind of cool. And then she went on, and again, just to kind of help you understand what we're studying right now. Let's see, where did she put this? Earlier, she said the mean was 2.54. And so what we're studying right now, notice right here, this is what's called a confidence interval. She said, I'm 98% confident that the real mean, and she should have even said, she shouldn't have just said the mean here. She should have said the population mean. The actual right answer to the question is somewhere between 1.99, roughly 2, and 3.1. So she recognizes, we recognize that we're taking a sample, and therefore it's just it might be wrong. What we're studying now is the fact that if you take sample after sample after sample, all the sample means would be normally distributed. And who knows which one she got here? She only did 1 sample. I mean, who has time to do 50 samples? She did 1. So she goes on and reports that, well, although I got 2.54 for my mean, the real mean, the population mean, could be as low as 2, maybe actually as high as 3.1. That's kind of cool. So again, that's what we're studying right now. And so notice, wow, that's kind of nice looking. Let's see, let's look at one other. This was kind of playful. She was interested in where she worked, Pacific Source. It's not 2 words. At Pacific Source, where she worked, she's just kind of curious. Nobody, in a sense, this isn't like money or the world's going to change, but it's just like, how many cups of coffee do people drink a day? And this is really fancy. Like this is beyond my skill set. Like this is really, she brought pictures in and so forth. Again, if you do this, do it because you're trying to get a job someday. Don't necessarily do it for me. Yeah, I'm going to give you a lot of points for the presentation side of it, but do this because, you know, what would you think if somebody showed you this, that they made this? Maybe she already has some experience with this, but if you've never done PowerPoint, it's super easy. You just have a bunch of pages, and just like you would copy and paste it into a Word document, you copy and paste it into these different pages. And so she chose coffee, conducted this survey. She had 61 employees. And that's interesting that it was only 30%. So basically 1/3 of people responded to that survey. And their answers were anywhere from 0 to 7. And notice she said 7+ because maybe some weirdo was like 13 cups or something and she didn't want to have this big gap in her survey. Here's a list of all the answers she got. Again, notice, isn't that classy looking? Like, I don't know, how did you do that? I don't know how she did that. She's better at PowerPoint than I am. But she reported the basic data. 1.95 was her mean. Again, isn't that probably the single most important number? Like, what was the average? Oh, about 2. But what's the standard deviation? What's typical to deviate from that? Again, a lot of you screwed that up on the last test. People still don't know what standard deviation means, and it's really going to hurt you in this section if you don't. It means although the average was 2, that doesn't mean everybody reported 2. As a matter of fact, it wasn't weird to deviate from 2, not just deviate, but from the mean 2 by 1.5 cups. And as you know, so it's typical to deviate from that by 1.5 cups. And then it would be unusual to be more than 2 of those standard deviations. So 2 of these 1.5s would be 3. 2 + 3 would be 5. 2 - 3 would be -1. And so it's unusual to be outside of -1 to 5. And she had some of those folks that were unusually high. So really, in the real world, these 2 numbers, standard deviation and mean, you're going to see those in magazines, kind of newspaper and TV all the time now, because those are kind of the 2 main numbers. And frankly, when you leave this class, I didn't make you be here. Some program wanted you to be here. That's kind of why right there. Do you understand what mean and standard deviation are? And as you can appreciate, again, bar graphs are huge because now all of a sudden you no longer have this pile of numbers. Notice she didn't have to make classes because she didn't have very many answers to her questions. Do you understand that? She only had like 7 answers to her questions. And so there was no reason to have classes. She just was able to make a bar for each one. And so again, visually super easy to see, well, exactly what we just said a second ago, which is, you know, 0 to 5 are the typical people, but there were some people that were outside that. So she also made a circle graph. And then some of the stuff we're again studying right now. Remember, her mean was 1.95. Well, she reported her confidence interval. That the real mean, because remember, she only got 30% of them. So all of her work was a sample because she didn't get everybody to respond. It could have been a population because she wasn't asking America, she was asking her workplace. And therefore it's a sample mean. And notice she used the correct symbol here because that's the symbol for population mean. So she's saying the actual right answer for this company, I'm 98% sure is somewhere between here because my study had an error of about 1/2 cup. That's what we're studying right now. So anyway, that gives you at least a sense of how this could work. I'll show you this really quick. This was kind of cool, I thought. I thought this was particularly cool just because it was a good idea. And this is what I mean about why I don't think you should present it in Excel. This was great though, but in her case, she actually works for the Medical Eye Center. Where's the make this smaller page? So she brought a graphic in for that. And her curiosity was because they do cataract surgeries all the time. She was just kind of curious, how old are people when they get cataract surgery? And so your work is a good place to actually gather your own data. And it's kind of fun if you can do that, and it might help you with your own job right now. So she was able to gather that data probably by asking somebody there, one of the data nerds or something. And so again, notice it's kind of cool to see this graph. Looks like, you got to over 64. That's kind of where you get cataract surgery. Kind of unusual apparently, since there's a very small bar to be between 48 and 51. Notice she had a lot of ages. Looks like a range of 48 to 85, and therefore she can't she can't have a bar for every single year. There'd be like 50 bars there or whatever. So she had to make classes, and you should be good at doing that. So again, you see a list here of mean and standard deviation and the 5-number summary and the lower fence and the upper fence. And because of the lower and upper fence, she did found one outlier, that 48-year-old, that was outlier low. Like to have cataract surgery when you're 48, that's really strange. That's something's going on there. That's kind of cool to be able to conclude that. But you see what I mean? Like, there's nothing wrong with that, but all you have to do is grab this graph, hit Control-C for copy, go over to a Word document and paste, and then it gives you a way to type stuff. Basically, in this format, she really didn't have any way to type and kind of explain anything that she might have wanted to explain. So it's kind of better to use Excel as kind of your workstation, and then you go put it somewhere else presentable. As far as your grade, I don't care if you do PowerPoint or Word docs as far as what you're doing in this class. Up to you. Any I mean, you haven't thought about this that much, but any rough questions about your thoughts on that? Nice and loud. I'm sorry, masks are making me can't hear you.
Oh, sorry. If you're retrieving data from the internet, what kind of
I don't care. If you find data on the internet anywhere, as long as you just give me the site for it. In the end, get some data. I don't care where you get it. So, yeah, good question. Okay. Little intro. If you begin thinking about that now, life will be good for you. All right, let's get back on track and talk about 8.1. I want to just dig deeper into 8.1. That's really all we need to do today. And I'm hoping to shut up in time kind of for, maybe a half an hour at the end. You can actually start jumping into the assignment because, as I've shown you, there's sometimes curveballs sitting in those assignments. And so 8.1, what we're looking at is the distribution. I need this to mean something to you. We're not sharing. Why aren't we sharing? Thank you. Your screen sharing, it says here. No, it's just small. This happened yesterday. It's like it's not very big. What did I do differently? Oh, is this? There we go. Is that what you usually see? Okay. We're talking about the distribution of, this is important, the sample means. 8.2 will be the distribution of the sample proportions. And so this concept is something that what we're learning right now is the rest of the class. This is chapter 8, but we still have chapter 9. So if you don't get this, you're not going to get chapter 9. And really, the only reason I even write 8.2 down here is because what is your data? What's your interesting question? Is the answer to it a number, a mean, or is it a percentage? My interesting question is, what percent of people have had COVID? Well, does it make sense that's kind of a 8.2 question? Because in the end, I'm going to go ask my question of people, and maybe I find out that 70% of people have had COVID. Well, 70% is a sample proportion. That's an educated guess. I did a study, but the right answer to the question is not 70%. That was a study. So these two sections are the same. It's just the idea is what is your data? Is the answer to your question a percent, or is it actually a mean or a number? So we're focusing right now on questions that have a number for an answer. How many days did it take you to get over COVID? That's going to be a numerical answer. What percent of people have had COVID? That's going to be a percent as an answer. It's just a question of, what your data happen to be. Okay, so big things that you need to understand about this, just to make sure that that is super clear. Shape. Now, again, probably the most important thing up here is that S right there. In other words, means, sample means. You did more than one sample. Therefore, if you graph all of those samples, then you're going to get kind of a bar graph, a distribution, a graph. What's the shape of that bar graph? It's going to be normal. Well, there's a small caveat to that that I didn't say yesterday that I want to get across to you now. It's not a super important idea, but it's normal if the original population is normal. Or you just check with lots of people. If your sample, and I'll explain what I mean by that, but if you have a tiny sample, so if you only sample like 4 people, does it make sense one person can kind of screw up that sample huge because they represent 25% of your mean? If you have a tiny sample, one person makes a big difference. But if you have 30 people, does it make sense one strange person's number will be absorbed by 29 other people? There's a lot of other people to absorb it. If you have a small sample, like 3, and your number is really weird, well, then the other 2 people probably can't fix that with their maybe more normal behavior. I'll show you what I mean by that in a second. So the distribution of, and I've got some more Excels to show you today to kind of get you to be able to visualize this. Again, what do I mean by the distribution of sample means? You take your own sample as those people did for their final project, and you get an answer to the question. One of the ones I didn't show you was another gal was like totally into snakes. And so she did one on like the weight of the mother python when she gave birth. How much did she weigh when she gave birth? And isn't that an unusual question that like only somebody that just loves snakes would be interested in? And so, but she does a sample of this, and that, again, that sample won't be exactly correct. I mean, there's 50 million pythons giving birth in the world right now, right? And so she checks with 30 of them, if you will. But if she checks with this 30 over here, then she gets an average weight. But then she checks with a different 30 over here, gets a totally different average weight. Do you understand that? I mean, you understand the concept that when you do a study, I've said this a lot, but I just want to make sure it sinks into you deeply because it's the foundation for everything we're doing from here on out.
Literally 30, like if it's 29 and less, it's not.
No, it's kind of a sliding scale. If you did it with 4, it would kind of be terrible. The larger and larger n gets, the more and more that distribution of sample means will look normal. So in a sense, it'd probably be better if I said greater than 30. And so it's kind of perfect. If it's 30 or more, like don't even think about it. But if you had 28, it's still going to look pretty normal. So in a sense, that's why I said on the final project, get 30 numbers, because then even if your original data is not normally distributed, then the distribution of the sample means still will be. That's, and again, I got something to show you about that in just a second. Matter of fact, maybe I should just show you right now.
So like 30 in each sample or 30 total?
30 of your sample is 30. In other words, you go ask 30 people. You go check with this 30 pythons, and then you check with a different 30 and a different 30 and a different 30 and a different 30. And what are you collecting every time? Just the mean. 30 pythons, what's that mean? 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 And so now my data is not individual pythons, it's this huge collection of means. I've got mean number 1 and mean number 2 and mean number 3 and mean number 4 and mean number 5. And now those means are my data. And if I made a bar graph of those with classes, it would look normally distributed. Well, if the original data was normally distributed, now think about the Python thing for just a second. Does it make sense to you that probably the birth weight of mother Python would be normally distributed? Probably. Wouldn't there be like kind of an average, and wouldn't lots of them kind of give birth around that weight, and then it'd be a little more unusual to be small and a little more unusual to be large? I mean, it sort of feels like it would be. Do I know? No, but it sort of feels like that would be the case. If that original data was normally distributed, then and your study doesn't need to be n as 30. You can just check with 8. Doesn't matter what the sample size is for you because the original data that it came from was normally distributed, but it isn't always normally distributed. Let's take a look at that right now. Please interrupt and ask lots of questions whenever you have them. Interrupt. Emphasize that. So effect of n on distribution sample. So again, this is just a simulation so that you can watch this in action. Now, why is this always in the way? Thank you. I'm done. Now I want you to stare at this for a second. Look at this data over here. This is the actual national study. This is huge. Somebody did a national study on the percent of households with numbers of children. Notice there weren't very many people that had 0. There were tons of people that had 1, tons of people that had 2, and then as you might expect, it starts tapering off. Now, would you agree that's not normally distributed right there? And it kind of makes sense that it wouldn't be, right? So this original data is not normally distributed. So the original data that you took it from, not normally distributed. Does it make sense here? It would be important then to, if you're going to take a sample, then you better check with 30 or more. That's kind of the idea. Now take a look over here at these 2 graphs. This is a person taking a sample with just 4 people. In other words, you're going to go ask 4 people, how many kids in your house, 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 and you're going to take the average. Notice the distribution of that is not normal. That's kind of what I'm getting at. In other words, we're going to do all this math based on a normal distribution, but we got to be sure it's normally distributed. If your sample size is only 4 and the original data is not normal, then you're not going to get a normal distribution. However, notice if you're at 20, and this is Tatisha's point, notice that I didn't say 30. But did you notice if your sample size is the same exact problem, it's just you checked with 20 people, and then you got your means. Again, do you understand if you check with 20 people, if one person had 13 kids, you have 19 other people to balance that out. And so that's going to make that mean not be quite as big as it would have been. But if you have 4 people and one of them says they have 13 kids, that's going to be a huge mean, no matter what the other 3 people say. And so notice this distribution over here, just because you ask 20 people, you still get a mean. It's just this person got their mean by asking 4 people, and this person got their mean by asking 20. Notice the distribution of all those sample after sample after sample. Remember, these graphs are a list of samples, not a list of answers to individual questions. Notice that's starting to look normal now. And again, to Tisha's point, 30 is the magic number to where it'll be kind of perfectly mathematically normal. But even if you creep toward 30, it's just going to get better and better and better. So watch, I'm taking samples here. Every time I push this button, I'm getting a new sample. So notice again, the blue graph, you're not getting a normal distribution. Whereas the purple graph is starting to look more and more and more normal. Now, take a look over here. You can't see this very well, but notice in the original data over here, notice the actual right answer to the question, the population mean is 2. And again, that's not really honest to say that's a population mean because you did not check with everybody. But if that's a national survey, you would assume at least they checked with 600,000 families or something, you know, something really huge. And so that 2 seems really reliable. What I want you to notice is, where do you see 2 over in this graph right here? This is one of the main takeaways for this section. Where do you see 2 showing up over there? In the middle. Exactly right. The center of the normal distribution, I realize these are small. Let me see if I can make them bigger. Format axis. Maybe I can just click it and hit up. There we go. That's more better. The center of the distribution of thousands and thousands of samples of size 20 that you took. Sample means, again, you throw the data away. You ask 20 people, you add them all up, divide by 20, you throw all the data away and you just keep the mean. And so that mean is made from people with 13 kids, people with no kids, all over the place. Every single study, every single sample of 20 gets a different answer. And then you just plot the distribution. Now, again, isn't it weird that one dude went out there and sampled 20 people and noticed there was one person that got a mean of less than 1.26. I mean, based on the graph, doesn't that look like, wow, I can't believe that happened? Most answers you got were, well, right here in the middle between 1.76 and 2.25. The center of this graph will actually tell you what the population mean is. That's the idea. This data came from a population mean of 2. And sure enough, if you do sample after sample after sample after sample, the center of that normal distribution, well, pretty close to normal, and is 20. The center of that will actually tell you what the population mean is. That's what's kind of cool. So again, the important thing is not so much, let's go do 50,000 samples. It's you're going to go do one sample, and what you don't know is your sample over here? Did your sample happen to be 2.6? You're wrong and you don't know it. Did your sample happen to be this tiny one over here that was 1.1 or something like that? Remember, it's really low, but you don't know it. It's not like the right answer is out there. If it was, you wouldn't be doing the study. That's the big picture. So I'm just hoping that this sinks in more and more for you as we go. So let me say a couple other things on the note sheet then. Okay. I'm getting better. So, do you have a sense of what I said right there for number 1? You have a bunch of sample means, plural, many, many means. A bunch of samples, and the shape, if you were to treat those sample means as though they were individual data points, you're actually going to get a normal distribution. Always, no matter what the original data was, if n is bigger than 30, and it'll be normal, no matter what n is, as long as the original population was normal, then it'll be normal and you don't even have to care what size your sample is. Second thing is center. If the mean of the distribution, the mean of that distribution is the population. Maybe I should even say it this way. Maybe the center of that normal distribution I don't know if this will show up in your assignment, but I'll just, again, mathematicians, and I showed you this yesterday, but mathematicians kind of turn this into a nifty little formula, and they say the mean of the samples, you take all of those samples and you find the center. The center of a normal distribution is always the mean. So the mean of all of those samples, again, not the mean of a bunch of individual numbers, but the mean of the samples, that's what that little X is doing down there, actually is the population mean. That's saying in a formula, in a sense, exactly what I just said right here. So we just saw in the distribution of all those samples of size 20, we saw the center of it was 2. Sure enough, that was actually the population mean. That's kind of cool. Third, did not show you this yesterday. Kind of the spread. In other words, the standard deviation. Now think about this really carefully. Does it make sense that if I went around with my little clipboard and said, how many siblings do you have? And I just ask individual people and I write down what they say. Does it make sense? I'm going to ask some people that are kind of outlier-ish. So most people are going to say, I have 1, I have 2, I have 3, I have 0. That's kind of what you're normally going to kind of hear. But you're going to hear somebody that says 12. I have 12 siblings. Whoa. So doesn't that feel like an outlier? It feels like kind of a big number. Now, if I do what you're doing on your project, which is I take all of those answers I got, oh, you said 1, you said 5, you said 3, you said 4, you said 2, and I just crunch those numbers, that person that said 12, especially if I didn't ask very many people, if I only asked like 6 people and one person said 12, that's going to make a huge mean, and it's also going to make a big standard deviation. In other words, that's a big deviation from what all the other ones were. However, if I ask 30 people and one person says 12, I have 12 siblings, there are 29 other people that are going to kind of calm that one down. Does that make sense? Now, if I go off, and again, what we're talking about now is not comparing person to person to person. We're talking about comparing sample to sample to sample. So then if I turn and say, okay, I'm going to go ask a different 30 people, then I'll get a whole bunch of different answers. But does it make sense the two means I get from that are going to be a lot closer to each other because you have 30 people to balance out kind of one unusual person? Does that make sense? So for that reason, the standard deviation of what we're talking about here, the sample means, not the standard deviation that we're used to, just sigma, but the standard deviation of the sample means is affected a lot by the sample size. Therefore, there is this formula. I'll show this on your note sheet, but there is this formula. And so just like this up here said, hey, the mean of the sample means is actually the population mean. This formula down here says, hey, the standard deviation, not the standard deviation of nothing, but the standard deviation of the sample means actually gets to be recalculated to be way smaller than it would have been. Let me just kind of ramble about that to kind of show you kind of what I'm talking about. So let's say you went and asked people number of sibs, and and so you start asking people, this person says 1, this person says 2, this person says 0, this person says 4, this person says 3, this person says 2 again, this person says 1 again. And then you get one person that says something a little higher like 6. And so it's a really small sample. You only asked 8 people there your question. And so that's not, not a very good study, but you asked 8 people. Now, because it's easy, I think I'm going to go ahead and type this in my calculator and actually get the standard deviation of this. Won't take me very long to do that. So 1, 2, 0, 4, 3, 2, 1, 6. And I say stat, one variable, statistics, list 1. And it tells me the standard deviation of these individuals. This is an important word here, individuals. This is all we've ever done in this class, is we had a list of data and we found the standard deviation of it. So the standard deviation of those individuals, I'm getting about roughly 1.8. No, I'll call it 1.9. I'm getting 1.9. And I won't write it down, but the mean I got was 2.4. Oh, maybe I will. So again, you can appreciate those are kind of cool numbers. And so it kind of looks right. Doesn't 2.4 sort of look like it's in the middle of that list? But you got a standard deviation of roughly 2. In other words, there was quite a, and that 6 caused a lot of that. Do you understand that? That 6 is what caused that standard deviation to be 1.9, almost 2. If that 6 wasn't there, it would have been a lot lower. If that 6 was kind of more of a normal number, like 3, that would have changed the standard deviation a lot. Can you feel that? Again, I use the word feel very decidedly. So this is the standard deviation that you're used to. It's of individuals. But remember, this was just one study of 8. So if I go do another study of 8, so I'll call that X1 and standard deviation 1 or something like that. Does it make sense if I did a second study, I'm not going to get 2.4 for the mean? Maybe because I didn't ask a person that said 6, maybe this next group, I only get something like 1.8 siblings for the answer. Does it make sense that the standard deviation, I'll just write a couple of them down here. So you did 4 studies. Does it make sense if I look at these numbers right here, the standard deviation? In other words, those numbers are all a lot closer. When I looked at the individuals back here, I was anywhere from 0 to 6. There was a lot of variation. But will there be as much variation with means? You see what I'm saying? If I ask 8 people, I find the mean and then I throw all the data points away. So I just left with these 4 means right here. Does it make sense those are going to be a lot closer together? Like it's very hard for one of these to be 7. How could one of these be 7? Well, then you'd have to have had like 7s and 8s and 9s like for every one of these. Does it make sense that's really not going to happen? So do you see how the standard deviation is much smaller? So what this is saying here is, hey, you get to recalculate the standard deviation. So let's do that. So if I ask for the standard deviation, not of the individuals, but of the sample means, I get to take my 1.9 and I get to divide by the square root of 8. And so I get a much smaller answer. Again, all I'm trying to get across is the concept here. So what is 1.9 divided by, and of course, when you divide by the square root of 8, you're going to get a smaller number than 1.9. Yes, 8 because n is 8. So notice this says the square root of n. So whatever your sample size was. And so in my case, I get 0.7 now. So when you did your sample of individuals, maybe the population standard deviation is 1.9. But will there be that much deviation, not comparing individual to individual to individual, but sample to sample to sample? There's not going to be near as much variation from sample to sample to sample. And so we get a much smaller number. Time is it? So let's take a look at your note sheet for this. I haven't printed this for you yet, but this is your last note sheet. This is what we're studying right now. So again, to reiterate, this says the mean of all of your hundreds of samples, the center of all of your hundreds of samples will actually tell you the population mean. Again, it's very confusing, but that is kind of cool that somebody wrote it that tight, that clean. And then what I just showed you right here. What is the standard deviation? Well, not just the standard deviation, but the standard deviation of all those samples you took. Again, we're comparing sample to sample to sample, not individual to individual to individual. You get to recalculate the standard deviation to be smaller than it otherwise would be. Now, why did I point at it over there? The standard deviation between samples is smaller than the standard deviation between individuals, and it's greatly affected by sample size. If you have a huge sample size, does it make sense it's just going to get better and better and better? Because again, a sample of 1,000 means one person with a crazy answer has 999 other people to mellow them out. You're not going to get near as much deviation. So that's all you should actually need to know, but let's now do some problems in this section that kind of pertain to those formulas so that you kind of can get the homework questions right. So in the end, this is kind of all you need to know to get lots of the questions right in this assignment. Okay, so let's just do some examples. And again, I'm kind of trying to prepare you for the homework assignment now. Or, to help you kind of see like what kind of math questions or like, what do you do with this? Good for you. You've made all your dumb little formulas, but what can you do with this? Okay, so let's just do this one. Let's say this is an interesting question. I can't remember if I looked this up or made it up, but I have written down here that battery life for a 9-volt battery. You probably all had that beeping go off in the middle of the night because your smoke alarm goes off. That's kind of annoying. And so here's the 2 facts about this 9-volt battery life. Notice that's a bold statement to say the population mean. In other words, that'll last for 50 hours. That's kind of a bold statement, isn't it? Like, how would you, that almost feels like a lie to me. Like, what do you mean you tested every battery ever made? But we're just going to say, well, we know that. Okay, fine. That's what the company told us. I don't know. Maybe they did do a lot of studies. Who knows? Awesome. And not only do we know that, but we also know the standard deviation of that. And can you appreciate there would be a standard deviation? Like, if does every single battery last 50 hours? Like, there's no difference in the lead and the acid and all the stuff that's inside it. There's no variation at all. No, there is variation. I wonder what that would be. Well, what I found or made up was 6 hours. Again, what does that mean? It means it wouldn't be weird to be 6 hours over 50, 56, or 6 hours under 50, 44. That would be super typical. And as we've said many times, it wouldn't even be unusual to be 2 of those over or under that. So that's good to know, right? Because that doesn't mean without that second number, you would think, oh, my battery will last 50 hours. No, it's not. The standard deviation is a super important second number here that says, no, there's variation. Actually, it won't be unusual for you to be anywhere from 62 hours all the way down to, what is that, 38? 38 to 62 hours is actually normal, typical. So a lot of variation in that. Okay, cool. So here's a question that you would have done on your last test. Like a 7-point, and you're going to see questions like this in your assignment, so be aware. So from 7.2, the question would have been something like, find the percent that last longer than, say, 58 hours. You just did this on your last test. So you would say, oh, that's normal CDF, normal cumulative distribution function. I list my lower limit. It was longer than 58. So I list my lower limit of 58 and my upper limit is some giant number. I'll say 999. Remember, these numbers are not discrete, they're decimals. And so I said longer than 58. Is it okay to put 58 here? I didn't say 58, I said longer than 58. In a sense, the answer to that is no. But because they're decimals, what number should I put there? 58.00000001, like not 59. You understand that? Because these numbers are decimals. So for that reason, it's actually okay to put 58 there because these are continuous numbers. They're not discrete. Just a side point. And then I list the mean. Was this the right order? Mean and then standard deviation. And then it pops out a percent. So maybe you're doing this with me. Maybe you're just watching. Normal CDF, lower limit 58, upper limit 999, 50 and 6. I got 9%. Now, I want to remind you of something. It would be important to kind of note that these battery lives would need to be normally distributed for us to do this, right? Isn't this based on normal? Remember, the data doesn't have to be normal, but doesn't this feel like it would be? Doesn't it feel like, you know, yeah, maybe they all cluster around 50 and then it's unusual to be way out from there. It feels like it would be normal, but you'll notice in your assignment, they're going to state that. And so, again, what's cool about this is, remember, we're predicting the future based on this. That's inferential statistics. We're predicting the future here. We're talking about future batteries, not just reporting what happened yesterday. So, you know, if somebody needs to know that, cool. Now, again, I think a more interesting question here would not be longer than 58 because everybody's happy if their battery lasts longer. Nobody complains. It'd probably be more interesting to ask, you know, which ones last less than 30 hours because then they're probably going to get complaints. And so if that percent was really low, then maybe it's like, oh, okay, we'll live with that. If it was kind of high, then maybe we better do something different. Maybe we better report that it isn't going to last 50 hours or, you know, something that doesn't make people mad. What would an 8.1 question look like? Again, notice what our data is. It's a number. It's not a percent. This person said, how long will batteries last? And therefore, the answer to that is a number. It's a mean. What would an 8.1 question be about this? It would be this. Find the percent, or I'm going to even say, find the probability that a sample of size 7 will have a mean value longer than 58 hours. Now, can n be 7 in this work? Remember our discussion before about 30? Can I only check with 7? Remember, the answer to that is we don't care what sample size is as long as the original data was normally distributed, then you don't have to check with 30. But if that original data wasn't normally distributed, then we'd have to have a bigger sample than 7. Remember, we're using the normal distribution to answer these questions. That's what normal CDF is doing. And so if it isn't normal, then we can't be using that function. So how does this problem change? Like, is that the same exact question? I mean, aren't I still asking? It's like, aren't I going to get the same exact answer? Like, but what changes? That's the thing I want you to understand. Before, we were ultimately talking about individual batteries. But now we're talking about like a pack of 7 of them. Does that make sense? You have a pack of 7, and now you're talking about it averaging more than 58 hours. The entire group of them averaging more than 58 hours. Again, with a group of 7, you might have one low battery that's like cruddy, but you have 6 other ones to kind of carry its weight. Does that make sense? What do I change about this? What do I do differently? It's still the same question. What's the probability that a battery, well, a sample of batteries will last 58 hours? Or longer than 58 hours? Well, it's still longer than 58, correct, correct. The mean is still 50, but is the standard deviation still 6? No, I get to recalculate it. Why do we have to recalculate it? There is 6 hours of variation battery to battery to battery, but is there 6 hours of variation sample to sample to sample? No, with the sample, you're going to get a lot less variation. That's what we saw right here. These 4 samples did not vary from each other very much. Remember, the original standard deviation was 2. Do those look like they vary from each other by 2? No, it's much smaller. So I get to recalculate this standard deviation. I don't use 6 here. I get to replace this with 6 divided by the square root of what? N, which in this case is 7. They took a sample size of 7. So I'm going to have a much smaller number there. Now you can just type that straight into your calculator if you want. You don't have to go figure out what 6 divided by the square root of 7 is as a decimal if you don't want to. Since I just hit second entry to retype the whole thing, so I'm just going to go back there and add a divided by the square root of 7. You might do this just to make sure you don't get it wrong, but so I just did this and I got 2.09. Please do this with me because some of you are still screwing this up. If you get 2.09, you should say something's wrong because what does normal CDF produce? It produces a percentage. What are percentages? They're between 0 and 1. What is this person doing wrong? Look closer at your answer. That answer is not 2.09. What is it? So the fact that it looks like 2.09, you should say something's wrong. Percentages are always less than 1. Then you look over to the right and you see, oh, there's a little -4 over there. Oh, okay, so that's actually not 2.009. It's moved the decimal point 4 places to the left. So it's actually 0.00209. Now compare these two numbers and just think about them. Again, there's like a third of your assignment is the questions like that. Compare those two. What's the probability that one battery will last longer than 58 hours? 9%. Pretty decent chance, right? But what's the probability that a 7-pack will average that high? Remember, what is the real average? The real average is 50. So, you know, what's the chance you have a 7-pack that actually shouldn't it average 50? Like, is it 50 the right answer for the average? You'd think that it would last 50 hours. What's the probability that a 7-pack will have an average, given that all the original numbers are around 50, meaning below 50 and above 50? That's how you got 50 for an average. What's the probability a 7-pack of batteries will average 8 hours over? Like, that's pretty tough, isn't it? Because you have 7 batteries that all have to have really high answers when the average is supposed to be 50. That'd be weird for 7 batteries to average 58. Well, notice that's telling you not going to happen. Your 7-pack is not going to average that high. That's way lower. So do you see how the sample size makes a big difference there? Just for the heck of it, what if n had only been 3? Does it make sense? You have a much better chance with only 3 batteries. You have a much better chance of averaging 58 because it doesn't take 2, and you could just have 1 crazy battery that was like 90 and that would average. So with 3, it's easier for this to happen. Does it make sense to you? I'm going to get a higher percentage this time. So if I redid this, everything is the same, except for this time, 6 is divided by the square root of 3. Again, I'm just trying to grow your intuition a little bit because I don't want you just to be a button pusher and have no idea what you're doing. Notice that's a little higher percent chance. You got a 1% chance. That could maybe happen. 1 out of 100. 7 packs might actually average over 58. That could happen because it's only 3 batteries. And I won't do this, but you can appreciate, you know, it's like, what if this was a 12 pack? What if that's a 12 pack? Again, doesn't that feel like that's never going to happen? Like the percentage is even going to be lower than 0.0002. So the key concept here is in 7.2, we are comparing battery to battery to battery, whereas the rest of this class, we're comparing sample to sample to sample. You try this one. I think I did look this one up. Anybody know anything about dogs? Does it take 9 months for a dog to be born? You know this. You are correct. Turns out the mean for dogs, they only have 63 days. We have 266 days. They've got 2 months. And it's like, bam, you're a parent. And as you, of course, would predict, that's only half the story. That would indicate every dog takes 63 days. As you know, that's not going to happen. There's variation there. That's what that's why you have to move on and also report standard deviation. That's why these 2 numbers are so powerful. Again, notice I'm sort of implying that I actually know the right answer because I didn't call that 63 a sample mean. I didn't call that standard deviation a sample, an S, I called it sigma. So I'm actually saying those are the right answers, like somehow I know that. But if you went and did it, it's the point of this section, if you went and did a study, maybe this is your final project, because you like dogs. If you went and did your own study for this and you checked with 83 dogs, and you probably could get this information from a vet, you know, not have to work that hard. It's not like you have to go collect it yourself. You're probably not going to get 63 days in 4 days, right? Because you did a sample, and so yours will be off. Yours won't get the same answer as this. So we're just talking about the shape of the distribution being normal. Can you appreciate this would also probably, like the last problem, be normally distributed? Wouldn't there be like lots of dogs that hung out around 63 and not very many that went way out beyond that? It kind of seems like that would be normal. Therefore, again, it's kind of cool. The original data, the population data was normal. Therefore, when I do a sample, I don't have to get to 30. I don't have to check 30 to make sure I have a normal distribution. I can just check anything I want. I can do 7 like we did last time. So I'll kind of write this in hieroglyphics just to be kind of quick. But again, you answer the same type of 2 questions. What's the probability that one dog will be less than, let's say, 59 days? What's the probability that your dog, which is the only dog you care about, right? It's your dog. What's the probability that one dog will have a gestation period for their puppies of less than 59 days? Secondly, what's the probability that a sample of 12 dogs will average less than 59 days? Do you see the difference in those 2 questions? I guess is what I'm getting at. A dog, a sample of 12 dogs. Big difference. 12 dogs, one weird dog is going to get mellowed out. The sample mean that you get The sample mean that you get with 12 dogs is not going to be near as affected by one weird dog. Come up with answers to those, write them on scratch paper. And I think I'll shut up after this and let you jump onto my open math and start wading into it. Did you get about 16% for the first one? There's a 16% chance. Now, again, what's important to know about this is if your dog was less than 59 days and you realize that was a 16% chance, you should relax from that, right? That's not a tiny percentage. Therefore, it's like, this isn't dangerous. 16% of dogs actually give birth in less than 59 days. And so I kind of have that, whew, okay, good. Everything's fine. I don't have to worry about it. Notice I'm able to predict that. I'm able to, if I'm the vet, I'm able to tell you, you know, as you're all freaked out, oh my God, it's supposed to go 63 days. Dude, relax. 16% of dogs are less than 59 days. Oh, okay. Whew, that makes sense. That's cool. We just did this on the last test, normal CDF. This time though, I said less than 59 days. So 59 was your max. Again, what did you put for, the logical thing would be to say 0. But remember, you probably should say negative 900 or something. I actually put 0 in there, but the mean is 63. And because it's one dog, the standard deviation is what it is. What do you get though if you do this with a sample of 12 dogs? You get 2.66. Again, if you're not paying attention, you don't notice the e to the negative 4. Oh, so the answer is actually 0.000266. Remember, the average is 63 days. So 63 days as an average comes from dogs with 64 and 5, and then dogs with 62 and 61, right? That's why 63 is the average. It's a bunch of numbers that collect around 63. So if you have 12 dogs, then how could you get a number as an average that was clear down to 59 when the right answer is supposed to be 63? Remember, this is what happens though when you take a sample. If you took a sample of 12 and you got 59, you would say, oh, the average is 59, but remember, you might be wrong. Notice this is saying kind of like that's not going to happen, man. What is that? Tenths, hundreds, thousands, that's 2 10,000ths or 3 10,000ths. So if that actually happened, I would think something was wrong. Does that make sense? Somebody's doing something wrong there. I mean, that's not going to happen by accident. And that's one of the things we're going to be discussing later in this class is something called hypothesis testing. Could that happen by accident? In other words, if my veterinary clinic had 12 dogs in and all of them were born in less than 59 days, the chances of that is really low. It's like, what's the doctor doing? Oh, he's squirting some kind of a drug into them. Oh, okay. So that makes sense now because that's not going to happen randomly. He's defending himself in court saying, hey, man, that can happen. It happens. And you're saying, well, yeah, there's a 2 in 10,000 chance it's going to happen. No, it didn't happen by accident. You're going to jail. And you see what I'm saying? Like this can sometimes be important stuff. What did you change? Only one thing. Instead of normal CDF of 0 and 59 and 63, you got to switch the standard deviation. You got to modify the standard deviation, make it much smaller. Again, I hope that makes sense to you because a sample of 12 dogs, their average is not sample to sample to sample. This 12 dogs compared to that 12 compared to that 12 is going to have a much smaller standard deviation. I never wrote down what it is, but just to kind of make note of it, 4 divided by the square root of 12 is only 1.15. And so this 4 is dog to dog to dog. It's super typical for them to vary from 63 by 4 days. But sample of 12 to sample of 12 to sample of 12, what is that going to vary from 63 days? Only one dog. Does that make sense? I'm sorry, only 1 day. Samples of 12 are only going to vary on average 1 day from 63. But dogs, individual dogs, they're going to vary by 4 days, but samples of 12, they're only going to vary by 1.15 days. And can you appreciate it just gets crazier from there? Like what if you did a sample of 78 dogs? I mean, if the right answer to this question is 63 days, then if you have a sample of 63 of 100 dogs, then isn't that the answer you're going to get for the average of 63? I mean, that. Okay, that doesn't mean there isn't curveballs in the assignment. So the rest of the time is yours to, if you're smart, you'd wade into that and see what you get. But you're free to do whatever you want. If you say, oh, I got this, I'll just go home and do it, then do it. Man. So any of you, I'll be wandering around, but I see a number of you guys online too. So you guys are more than welcome to pull up my open math and start dinking with it too. You guys can ask me questions probably via chat. I mean, let's see, would I hear you if you talked? I actually don't know. I think I would. I think what's that?
Yesterday.
What didn't? Oh, you tried to talk?
Yeah.
Oh, interesting. That's good to know. Let's see. Yeah, it looks like they're all muted. Are they?
I unmuted myself.
Yeah, you unmuted yourself.
Your computer's muted.
What'd you say?
Oh, your computer is
You're on the
muted.
right hand side, there's like a symbol on the bottom. Like, you can see if I play music or something.
Yeah, so anyway, you guys online, you can attempt to talk. We're not sure if that works or not. I just unmuted that, which could be an issue. I can maybe not hear it. So I'm going to shut up and wander around.